Hello friends, welcome to our channel. In previous videos, we discussed about metric spaces and some results based on metric spaces. In today's video, we will discuss the new topic, non-linear space. So we will discuss the definition of linear space, and then non-linear space and some results. Before discussing the definition of non-linear space, we have to discuss the definition of vector space. What do you mean by vector space? Let X be any non-empty set and K be the field of scalars, then X is said to be vector space over the field K with two binary operations known as vector addition and scalar multiplication and satisfying the following properties. 1. X is an abelian group with respect to binary operation addition, that is, first X is closed with respect to addition, UV belongs to capital X, then U plus V is belongs to capital X for every UV belongs to capital X. Second, associative property. Let UVW belongs to capital X, then U plus V plus W is always equal to U plus V plus W for every W belongs to capital X. Third, existence of identity belongs to capital X, then there exists a unique element 0 belongs to capital V such that u plus 0 is equal to 0 plus u is equal to u for every u belongs to capital X, where 0 is called identity element of capital X. Fourth, existence of inverse. Let u belongs to capital X, then there exists a unique element minus u belongs to capital X such that u plus minus u is equal to 0. Minus u is inverse of u and vice versa. Fifth property, commutative property. Let u v belongs to capital X, then u plus v is always equal to v plus u for every u v belongs to capital X. Then X becomes an abelian group with respect to addition. Second, scalar multiplication properties. Let u is belongs to capital X and a is belongs to k, then a into u is belongs to capital X for every u belongs to capital X and a belongs to capital K. This binary operation is called external binary operation. Also known as scalar multiplication operation. This operation the following properties first property, a into u is equal to u for every u belongs to capital X and 1 is belongs to K. Second, A into U plus V is equal to AU plus AV. For every A belongs to K and UV belongs to capital X. Third, A plus B into U is equal to AU plus BU. For every AB belongs to K and U belongs to capital X. Fourth, A into B into U is equal to A into BU. For every AB belongs to K and U belongs to capital X. If the set X of vectors satisfying the above properties over the field K, then X is called the vector space over the field K. It is generally denoted as X is a vector space over the field K. Note, X is called a real vector space if the field of scalar is the set of real numbers that is K is real X is called complex vector space if the field of scalar is the set of complex numbers that is K is equal to C, where C is set of complex numbers. Now, the next we will discuss the definition of normed linear space. In a non-linear space, we see normed, that means there is a function, is a norm function on the linear space. So let capital X be the linear vector space over the field K a norm function on capital X is defined as norm of function x to var satisfying the following properties. First property, norm of x is greater than equal to 0 for every x is belongs to capital X, and norm of x is equal to 0 if and only if x is equal to 0. Second, norm of x plus y is always less than equal to norm of x plus norm of y for every x y belongs to capital X. This property is known as triangular inequality property. Third, norm of a into x is equal to modulus of a into norm of x for every a is belongs to k and x is belongs to capital X. Then the linear space X is called a non-linear space over the field capital K. Next, semi-normed space. Let capital X be a linear space over the field capital K and norm is a function from x to r satisfying the following properties. First, norm of x is greater than equal to 0 for every x belongs to capital X. Second, norm of x plus y is less than equal to norm of x plus norm of y. Third, norm of a into x is equal to modulus of a into norm of x for every a is belongs to k and x is belongs to capital X. There is a small difference in semi-norm space and norm space. In norm space, in first property, norm of x is greater than equal to 0 and norm of x is equal to 0 if and only if x is equal to 0. But in semi-norm space, norm of x is greater than equal to 0 for every x is belongs to capital X. We have to exclude that norm of x is equal to 0 if and only if x is equal to 0 in a semi-norm vector space. The next theorem, every normed linear space is a metric space in previous lectures we discussed about metric space in detail. In today's lecture, in this theorem, we will discuss that every normed linear space is a metric space. That means a norm space which satisfies all the properties of metric space also, then it becomes a metric space. Proof. Let X be any normed space that is X norm of with norm function. We define a function d on x cross x to R defined as d x1 x2 is equal to norm of x1 minus x2. We shall prove that X is a metric space with metric D. That is, D satisfies all the properties of metric. First, by the definition of D, dx1 x2 is equal to norm of x1 minus x2 which is always greater than equal to 0 for every x1 x2 belongs to capital X. This implies dx1 x2 is greater than equal to 0 for every x1 x2 belongs to capital X. Again, if dx1 x2 is equal to 0, this implies norm of x1 minus x2 is equal to 0. This implies x1 minus x2 is equal to 0. This implies x1 is equal to x2. Hence, dx1 x2 is equal to 0, then x1 is equal to x2. Conversely, let x1 is equal to x2, then x1 minus x2 is equal to 0. This implies x1 minus x2, its norm is equal to 0 norm, which is equal to 0. This implies dx1 x2 is equal to norm of x1 minus x2 is equal to 0. Thus, if x1 is equal to x2, then dx1 x2 is equal to 0. This implies dx1 x2 is equal to 0 if and only if x1 is equal to x2 for every x1 x2 belongs to capital X. Second, let x1 x2 belongs to capital X, then distance between x1 x2 is equal to norm of x1 minus x2, which is equal to norm of minus 1 into x2 minus x1, which is equal to modulus of minus 1 into norm of x2 minus x1. This implies dx1 x2 is equal to norm of x2 minus x1, because modulus of minus 1 is equal to 1, which is equal to d of x2 x1. This implies dx1 x2 is equal to d x2 x1 for every x1 x2 belongs to capital X. Thus, D satisfies symmetric property. Third, let x1, x2, x3 belongs to capital X. Consider distance between x1, x3 distance between x1, x3 is equal to norm of x1 minus x3. We can write it as norm of x1 minus x2 plus x2 minus x3. Add x2 and subtract x2. There is no change, which is less than equal to norm of x1 minus x2 plus norm of x2 minus x3, which is equal to dx1 x2 plus dx2 x3. Thus dx1 x3 is less than equal to dx1 x2 plus dx2 x3. So D satisfies triangular inequality property. Thus D satisfies all the properties of metric on X. Therefore XD is a metric space. Hence every normed linear space is always metric space. It is sufficient for today's. In the next video, we will discuss some examples of normed linear space, some results based on normed linear space. So keep in touch, watch our videos and subscribe our channel for more results based on these topics. Thanks to all. Have a nice day. Bye bye.